the time you took to put that together and share it with us. As Jeff said, we'll hold the questions until after Ed's presentation, and Jeff did segue well into that because Jeff mentioned ASTM, and we're very glad to have Ed join us. Ed Eaton's joining us on the stage now, and well known to many of you, but if you don't know Ed, he's one of the chairmen at ASTM International, and he's responsible for the committee that covers diesel fuel, antifreeze engine coolant, and ISO 22241 diesel exhaust fluid. Ed's been in the industry for more than 30 years, and he's been involved in with OEMs, engine manufacturers, suppliers, and others. So as I said, he's chairing the technical committee D15, and he's been involved in tackling some of the gaps and I guess shortfalls of some of the other, especially the ISO regulation, and that's the particular topic he'll be tackling with us today, is to look at what ASTM is doing to fill in the missing aspects of what we see already in place that comes through from ISO, and just his experience of what ASTM has been doing with diesel exhaust fluids. So very glad that you could join us, Ed. Thank you very much for taking the time, and go ahead. We look forward to hearing from what you see from the point of view of ASTM.
Yeah, thank you very much. Are we on? There we go. So thank you very much for the opportunity of meeting. The group at Integer has asked me to talk about some of the activities that ASTM Committee D15 is involved in relative to diesel exhaust fluids. So to that end, ISO and ASTM International are both standards settings organizations. Both are now global societies, and while ISO has historically been active in Europe and European OEMs have followed ISO standards, in North America, ASTM had traditionally been that same kind of organization. Today, because the automotive market is really a global market, both organizations are still active and have found a way to respect each other and work in some cases together. So you'll sometimes see ASTM International standards cited, you'll sometimes see ISO standards cited. One of the big differences is that ISO meets much less frequently than ASTM. So even though ASTM standard setting is sometimes referred to as glacial in its speed, it is less glacial than the ISO standards. Structurally, ASTM International consists of a number of subgroups. One of the groups is a liaison that works directly with ISO. There is also a proficiency testing program which has stewardship of all of the testing standards that ASTM publishes, and there is a diesel exhaust fluid test program. And then there is a division of the overall organization into the technical committees. So I am a technical committee chair, the D15 chair. D15 is the committee on engine coolants and related fluids. So pretty much if it's not a lubricant or a fuel, which is the stewardship of D2, then it falls into D15. The committee, D15, is then subdivided into subcommittees, and there's a subcommittee on diesel exhaust fluid, which Joe Franklin chairs, and that is D1525. Joe's going to join us on the panel committee later. So, some assumptions of things you probably already know. Wrong button. There we go. Diesel exhaust fluid it's basically a very simple fluid, urea and water. It is used in the selective catalytic reduction system to reduce NOx. It can be made from either pearl, which is a solid, or a liquid urea, and very, very, very pure water, typically at 32.5%, but as you know, there are two other concentrations that are commonly worked with. The urea was readily available because it was being made and used as fertilizer, nitrogen fertilizer, but in this case, it has to be a very, very pure form of the urea. And the blending water also has to be very, very pure. So these are the issues, is the purity of the urea and the purity of the water. Contamination is possible either from manufacturing processes being such that contaminants can enter that system, but you can also have contaminants enter the diesel exhaust fluid from during transportation, during blending, from water that hasn't been purified properly, and even at the consumer level, if there's storage at a fleet site or something like that, environmental pollution can drift into a tank. The committee, D15, serves diesel exhaust manufacturers and users. So we have both kinds of folks that are members of the committee. We recognize ISO 22241 as the primary global specification and as the provider of the referee test methods. So what our role is to respond more quickly to the needs of the manufacturer and user community by providing additional test methods or specifications that are useful in day-to-day applications that the ISO 22241 specifications don't necessarily lend themselves to. The subcommittee identifies opportunities for field test methods that are useful for quick, cost-effective DEF testing. Now, we've been really, really active trying to identify this kind of thing because there are a lot of requests from owners of fleets, owners of agricultural equipment, and other DEF operators who, when they see some kind of an alert on a dashboard, for example, that DEF quality is low, they want to be able to somehow test the fluid and see whether or not they can confirm or refute that there's a problem with their DEF. We also look for omissions in the test methods or possible alternatives, and we bring those to the industry for discussion at ASTM, where there are participants from the manufacturers, and they're very, very capable people. This is a picture of a very, very bright white filter material through which some diesel exhaust fluid has been filtered at a production plant. And as you can see, it is no longer bright white. So automotive grade urea was mixed with water and filtered through this filter. And what you will see is a visual indication of some of the things that we pick up when we do testing and we have non-conformance issues. As Jeff said, the number one is high metals content. That's the one that if it's probably a little bit more than half of all the non-conformances is some sort of metals contamination. The second one is incorrect urea concentration. And it's important to understand that when we say incorrect urea concentration, that's not what shows up on our refractometer. That's part of the equation. But you have also another molecule, which is biuret. And the biuret factors, it looks like, to a refractometer, it looks like urea, but to an SCR system, it doesn't work like urea. So you have to measure all of that. You have to measure the biuret and subtract out the biuret to calculate the actual urea concentration. Another one is excessive insolubles. This is just basically dust or other foreign matter, often inert, that's in the urea and can cause a problem in the DEF. High phosphate or aldehyde concentrations in inadequate alkalinity, which affects the shelf life of the product. In order to measure metals in the laboratory using the ISO test method, we use an ICP, inductively coupled spectroscopy. And this is, again, the number one problem group. Unfortunately, right now in the field, we just don't have a test method to measure these. And that's because detection limits are very, very low. There are 10 metals in this group, each with limits below 1 part per million. So getting something that you can truck out into the field and find these kinds of tiny but important contaminations is difficult. So the precision has to be very high. An ICP, if you don't happen to be involved in the industry, is a six-digit kind of cost. $150,000, $250,000 is what it costs to buy one of these systems brand new. Urea concentration, as I mentioned, is not just a question of refraction. We use a bench refractometer, which is quite a bit more precise and repeatable than a handheld refractometer, but still the same concept of light bends through a liquid. There is a handheld refractometer method that we've established at ASTM to provide something, at least, in the field that you can use to give a rough idea of whether you've got a bucket of water or a bucket of diesel exhaust fluid, and that is ASTM D7821. These are very inexpensive units. In fact, I found one on eBay for $13. So, you know, something is better than nothing, but the problem is that the ISO method also requires a test by digital density meter and a Bayer-Red analysis in order to get the final ISO number. And that's not possible to do in the field right now. The Bayer-Red concentration, here are the two molecules. On the left you have urea, on the right you have Bayer-Red. Bayer-Red is essentially a combination of two urea molecules. But when you combine them, they're no longer effective in a selective catalytic reduction system. So the lab method that we use currently is a titration. It's a colorimetric titration. You put it in a spectrophotometer that reads at 550 nanometers with a 50 millimeter. Okay, obviously this is not something that's going to be field friendly, right? So what do? Well, you may have seen on television these little ampoules that contain reagents that drug agents use. They put a sample of a drug in, they break the reagent, they shake it up, and it comes up with a color. That kind of thing can't specifically tell you how much Bayer-Red is there. But that kind of a thing could possibly be made to tell you if any Bayer-Red is there. So that is a possibility that, that could be researched and looked into, problem being whether it's cost effective for somebody in the field to use. But scientifically, that would be possible. The other thing is that Bayer-Red's insoluble. So if you see a lot of floaties hanging around, you know, we don't know exactly what they are, but they're not supposed to be there. In the insoluble lab method, we use a lab-grade filter paper. We filter out anything that can be filtered is designated as insoluble. And then the paper is dried and weighed. It's a 0.8 micron filter. In the field, again, this is not a field-friendly situation. You can't dry something the way it has to be done in a lab, and you don't have balances that can measure weight changes to that precision. But you can look at the fluid in a clear glass vessel of some sort, and you should not see anything. It should be a water white, you know, platinum white, completely clear fluid. And if an end user can see something in the fluid, that would be cause for further testing. Phosphate, this is an important subject because it is being considered for revision into the ICP. That would be so important in terms of turnaround time and cost for laboratory purposes. Right now, you have to weigh the sample out, you dry it, and you actually incinerate it to create the ash, which you then dissolve in an acid, and then that acid is mixed with a reagent, and that is put into a spectrophotometer, this time at a different wavelength, and that's how you measure it. Well, that's not field friendly either, but using an ICP would eliminate the need for this method, and you would be able to get the potassium, which is part of the phosphate, and be able to get it that way.
ICP?
That was the inductively coupled
The other
earlier, yes. The big piece of equipment, the expensive piece of equipment. You can read this as well. Aldehydes, again, here you have a titration of the DEF with sulfuric acid, colorimetric indication at 565 nanometers. Whoops. And this is, again, sorry, got ahead of myself. Not something that's very field-friendly, but could possibly be a candidate for some sort of an ampouled development that would be something that would qualitatively tell you whether or not there was an aldehyde present. We're down the line now as to how many of these kinds of variances you see. So the probability that you would be able to cost justify something like this from a developmental point of view is very low. And then finally, the least detected nonconformance is alkalinity. In the ISO test method, whoops, you do a potentiometric. Let's come back. Touchy, there we go. Potentiometric titration is using a conductivity meter and so forth. Here you actually do have something pretty easy, because while there's nothing that's actually on the market to measure the alkalinity of diesel exhaust fluid, we do this all the time in engine coolants. And measuring pH or reserve alkalinity using a test strip is quite possible. And I'm actually surprised this hasn't been done. Although, again, the probability of a failure is low. What else is happening in the market? If you look over the last few years, and those of you who have been in the business of selling DEF have probably noticed a couple of things. One is relative to the time it takes to turn around an ISO 22241 protocol, and the other is the cost that is involved in turning around a 22241 protocol, have both dropped precipitously. So since 2010, when the turnaround time was about 14 days and cost about $1,400. We have seen dramatic drops, and if the ISO 22241-17 is adopted the way we currently think it's going to be adopted, this will continue to happen. But today, you should be seeing a cost somewhere in the $500 range, and you should get the data back the next day. That's the standard, and with the new protocol, you probably would see that tightened up even a little bit more. So it's a huge improvement compared to where it used to be. In the future, in quality control, 22241 describes and dictates the official test methods. That will continue to be the case, but at ASTM D15, we hope to provide some quick and dirty help test methods to make field testing at least possible. The collaboration between ISO and ASTM continues. Problem with DEF contamination between the blending plant and the user have been reported. So this transportation link or delivery link, you do have the time period when the vehicle, especially a bulk delivery vehicle, is being offloaded into a storage tank. What happens there? Is it a windy day? Is it Western Arizona where there's famous Arizona road dust roaming around? We're talking about such low levels of contamination that become important that it is conceivable that in the transportation and delivery processes, we would want to have some way of measuring whether everything was still okay. Users want to screen the DEF deliveries for quality. Right now, they do have refractometer methods. We would like to try and give them something a little bit more valuable, because the DEF does leave the plant typically at 32.5%. So it's not going to change much unless it's somehow contaminated or stolen. ASTM has developed the field test for refractometers. We're looking for new things. And independent laboratories have cut the costs and reduced turnaround times dramatically so that they make themselves more of a candidate for testing than they ever have been before. You can get timely, cost-effective information from independent labs. Okay, that's all I have, so we can I guess, move on to the... Thank you.
Thanks, Ed. I'm going to invite the other two panelists to the stage.